So, welcome you all in my next lecture. So, in this lecture, I will talk about the notions of differentiability of real valued functions of vector variable. In my last lecture, I talked about the notions of differentiability of vector valued functions of real variable and a couple of applications, but now I will talk about the notions of differentiability of real valued functions of vector variable, and there you will see the natural kind of, or the definition is not so natural from the real valued functions of real variable. You need some special things or some non-triviality, but before that maybe I will just bring it down to a very kind of an easy case, and there I will talk about some notion of derivative. Then I will show those are called partial derivatives, directional derivatives, and then there will be a concept of total derivative along with chain rule and higher order partial derivatives. Okay, so this is the one. So now I want to talk about the notions of differentiability for, you see I have written differentiation of scalar valued functions of vector variable. So now look at the range, this is R, and what is the domain? Its domain is a subset of Rn, some set S. I will say that this S is an open subset of Rn, that I already discussed. What do I mean by open set? If I have a functions like that, like from set S open subset of Rn to R, then what sort of notions of differentiability you will have? Of course, you can see that like in the real case or single variable case, like if I have functions from R to R, if I have functions from R to R, the notion of differentiability, you know that you cannot easily extend in this setting, because once we have the talk about the differentiability, this is nothing but limit say h approaches to 0, f of say x plus h minus fx divided by h, and this is nothing but derivative of f at x. Okay, but look, this is the quotients I am talking about. H is coming from where? From R. So then there is a concept of divisions. But however, if I have a functions from Rn to R, then there is no such kind of divisions. So therefore, this definition you cannot easily extend. So you need something different to talk about the differentiability of f from Rn to R. Okay, so I will define that. Before that, let me see what are the possibilities or what are the things I can talk about in this context. That means functions from Rn to R. Okay, so this is the learning outcome. So in this lecture, I think, well, we will learn the differentiation from a function f Rn to R, where S is an open set. So what are the concepts we will have? So I want to talk about the notions of differentiability for functions f from Rn to R. So these are the concepts will come: partial derivative, directional derivatives. Then I will talk about the kind of interplay, or I should not say interplay, like partial derivative versus continuity. That means existence of partial derivative implies the continuity of the functions, or existence of the directional derivative will say the continuity of functions, and vice versa. Those kind of things I will discuss. But before that, I need to introduce what do I mean by, or what are the concepts called partial derivative and directional derivative in this context. Okay, so I have written, so differential calculus for a functions f from Rn to R. Suppose you have a function f from Rn to R. So these are the questions I want to raise in this setting. What are the things? First, what does it mean? So first one, what does it mean to say that f is differentiable? Of course, I need to say. Second one, how to define differentiability of f at the point x0 in Rn or in S? How to determine the derivative of f at x0. So these are the wish list. So of course, if f is differentiable, that means we know that it should imply the continuity. It is indeed the case. And of course, if I have sum of two differentiable functions, product of two differentiable functions, of suppose composition of two differentiable functions, whether that I can have that properties in that setting as well. So I mean, given functions, whether sum of two differentiable functions is differentiable, product of two differentiable function is differentiable, or composition of two differentiable function is. So these are the things I will talk about that. Okay, so let's first talk about the notion of partial derivative. So what is that? So I am starting with the function f from, instead of Rn to R, because Rn to R it will be a little complicated. So at the beginning I am talking about a function f which is a subset of R2 to R. So that means I have a functions which defines on some open subset of R2 and taking values in R. So that's what I have written. Let f of xy be a real valued functions defined on an open set S in R2. Then what I am doing, keeping or fix a point P0 which is x0 y0 in the set S. Then there is a notion of what is called partial derivatives of the scalar field f. So this function sometimes called scalar field actually. It's taking values in R and domain is in Rn. what I am saying is that I am saying that okay, partial derivative of small f with respect to the variable x at the point p naught, which is nothing but x naught y naught, is, this is the notations del f del x at p naught, and is defined by, this is limit h approaches to 0 f of x naught plus h comma y naught minus f of x naught comma y naught divided by h. So what I am doing in this case is the following. So what? So I have a functions f from R2 to R, right? So I am keeping a point p naught which is fixed. That means x naught y naught coordinate is fixed. What I am doing is that I am defining a functions capital F, okay, capital F, I am fixing a functions capital F from where to where. I am fixing a capital F, define a functions F from say R to R. And what is that? The functions, since x naught y naught is fixed, what I am doing is that I am considering this function x goes to f of x comma y naught. Y naught is fixed. So that means once y naught is fixed, I am varying x. So now I am considering the functions capital F from x to f of x comma y naught. So this is a function from R to R, right? So now since I have a functions capital F which is from R to R, then I can talk about, or I know the notions of differentiability in that setting. So now if I suppose assume that my functions capital F is differentiable, say at the point x naught, okay. So y naught I am keeping fixed. Then I am thinking about as a function of single variable x goes to f of small f of x comma y naught, and suppose my function is differentiable at the point x naught. Then what is the derivative of capital F prime at x naught? What is the derivative in the single variable case? Very easy, limit h goes to 0, capital F of x naught plus h minus capital F of x naught divided by h, right? If I have a functions from R to R, if I want to talk about the differentiability of capital F at the point x naught, this is the formula we know, right? You just replace it, but capital F is given. I am keeping y naught is fixed. I am thinking about a function from R to R. Just replace this. What is it? This is limit h approaches to 0. What is capital F of x naught plus h in terms of small f? This is f of x naught plus h comma y naught minus capital F of x naught, which is f of x naught y naught divided by h, and this is exactly this object. So that means what I am doing is that I am starting with the functions f from some subset of R2 to R, and I want to talk about the partial derivative of f at the point x naught y naught, okay. Then what I am doing, of course I am talking about the partial derivative of f with respect to x, I should say, at the point x naught y naught. What I am doing, keeping y naught is fixed, considering the function x goes to small f of x comma y naught. Of course, this is a function from R to R because I am varying only x in R, okay, and I am getting f of x comma y naught since the range of small f is R. So therefore, it is a function from R to R, and then I want to talk about the derivative of capital F at the point x naught. That means the derivative of the functions capital F, which is a function from R to R. If it is differentiable at the point x naught, then I am saying that this is nothing but the partial derivative of small f with respect to x at the point p naught, and this is exactly the definitions. So therefore, the partial derivative of small f with respect to the variable, that is very important, with respect to the variable x at the point x naught y naught, this is the notation and is defined by this is one. If this limit exists, that means limit h approaches to 0, f of x naught plus h comma y naught minus f of x naught y naught divided by h. That means keeping y naught fixed, think about it as a function from R to R, and then talk about the differentiability on the first variable. This is called partial derivative of f with respect to x at the point y naught, provided this limit exists. Similarly, parallelly, you can think about that. Okay, instead of keeping y naught fixed, if I keep x naught fixed and vary say y, that means again I can think about as a functions. What sort of function you can think? Again, I can think about a functions, say g functions, which is again from R to R, and what sort of functions? This is y goes to f of x naught comma y, and then talk about the differentiability of derivative of g at the point y naught. Then you will end up with this. Okay. So again, the partial derivative of f with respect to variable y. So when I am talking about the with respect to variable y, it means it is automatic that I have to keep the first variable fixed, that means x naught is fixed. Okay. So at the point p naught is equal to x naught y naught is nothing but this is the notations del f del y at the point p naught, and is defined by this limit. So that means find the limit as k approaches to 0 f of x naught comma y naught plus k minus f of x naught y naught divided by k. That means since I am talking about the partial derivative of f with respect to variable y, then it is automatic that I should keep the first variable fixed at x naught and then think about the functions from R to R and then talk about the differentiability in the second variable, and that is why this is exactly the case. If this limit exists, I will say that partial derivative of f with respect to y at the point P naught is exist. Okay. So that means what I am doing in that case actually even if I have a functions from R2 to R, I want to talk about the differentiability of these functions at the point P naught, which is nothing but x naught y naught. So what I am doing is that, so if I want to talk about the partial derivative of f with respect to x, that means I am keeping the y naught variable fixed, think about the functions from R to R and talk about the differentiability. If I want to talk about the partial derivative with respect to y variable, I am keeping the variable x naught is fixed, x variable is fixed at this is at x naught, and I want to talk about the differentiability in the second variable. So that means actually what I am doing is that I am restricting myself, keeping one variable fixed, making a functions from R to R, and I know the differentiability of R to R, and that's how I am giving the notions of partial derivative with respect to x and with respect to y. Okay, this is the pictures I have taken. So this is explain the partial derivative of f at x naught y naught. It's very nice interpretations for partial derivatives. And what is that? So look, first one is that, so that means partial derivative of f with respect to x at the point x naught y naught is the slope of the tangent, is the slope of that. In the single variable we know if I have a derivative is nothing but the slope of the tangent, but in this case what will happen, so it's the slope of the tangent of the curve. So that means if I have a function f of f is a map from R2 to R, so that means consider the curve C1 which is z is equal to f of xy, then it will give you a surface right in R3. And what you do is that once you have a surface z is equal to xy, consider the plane y is equal to y naught, because I am talking about the partial derivative of f with respect to x, that means the second variable fixed, that means y is equal to y naught. So what you have a z is equal to f of xy, it is a surface in R3, you have a plane y is equal to y naught. So that means if you have a surface and you have a plane, then it should cut in a curve, okay, and that curve I am denoting at C1. Look at this picture. So this is my surface, so this is my surface, okay, and what is my plane y is equal to y naught? So this is my plane. So that means if I have a surface and if I have a plane, it curves on a curve. So and that is my curve C1. And then what is the corresponding partial derivative of f with respect to x at the point x naught y naught? This is nothing but once you have a curve C1, so consider this point, this is the point, this is x naught comma y naught comma f of x naught comma y naught. So this is x naught y naught comma f of x naught y naught, and this is nothing but the slope of this tangent. So this is the tangent, this is the slope. So that means I can interpret the partial derivative of f with respect to x at the point x naught y naught in this way. It is nothing but the tangent to the curve. Which curve? So consider the surface z is equal to f of xy, consider the plane y is equal to y naught, it will curve in a curve, and think about the tangent or slope of the or tangent to the curve at the point x naught comma y naught comma f of x naught y naught. What about del f del y at the point x naught y naught? Similar thing happen, because I am talking about the partial derivative of f with respect to y variable. That means I have to keep the first variable fixed, that means x is equal to x naught, and then similar kind of things will be there. Then consider the surface z is equal to fxy, okay, and since the first variable is fixed, consider the plane x is equal to x naught, x is equal to x naught. That means the plane x is equal to x naught and the surface z is equal to f of xy, they will cut in a curve that I am denoting as C2. And now consider the points x naught, y naught, f of x naught, y naught. This is nothing but the slope of the tangent at that point. So I just kind of given a picture here. So this is my surface, right? This is my surface, and this is my plane. Okay, x is equal to x naught. This is my plane. So they will have this curve here, and this is nothing but a slope of this tangent. This is the point x naught, y naught. Okay. So this is nice actually. So that means once I have a partial derivative with respect to x or with respect to y, you just consider the surface z is equal to f of xy, and depending on which partial derivative we are talking about. If I talk about partial derivative with respect to x, consider the plane y is equal to y naught. If I want to talk about partial derivative with respect to y, consider the plane x is equal to x naught. Then there will be intersection, it will give you a curve, and then it is nothing but the slope of this tangent at the point x naught y naught comma f of x naught y naught. That is the kind of interpretations for partial derivatives. Okay, so these are the kind of further explanations on partial derivatives of f at the point p naught equal to x naught y naught. What I am saying is that del f del x at the point x naught y naught gives the rate of change of f with respect to x at x naught when y is held fixed at the point y naught. So that I just explained now. So that means you have to fix y is equal to y naught, that variable, second variable fixed. Then it is nothing but the rate of change of f with respect to the first variable x at x naught. Similarly, another way is that del f del x at x naught y naught is basically rate of change of f in the directions I cap. Well, since I am in actually it's an R2, that means it will have an orthonormal basis conjugation of two vectors, that means you have a x direction, you have a y directions. So it says that del f del x at x naught y naught is basically the rate of change of f in the directions I cap 1, 0. So that means if this is my R2, that means I am talking about these directions. Okay, so that is nothing vector E1 at x naught y naught. Okay, so what is this? This is the formula del f del x at x naught y naught, which is nothing but same formula I am writing in this way. Limit t approaches to 0, f of p naught, capital P naught plus t E1 minus f of p naught divided by t. So you can write it, you can easily get it what I am trying to say. So p naught is given x naught y naught, right? So you write it here. So this should be like f of p naught means x naught y naught plus t E1. T E1 means t comma 1 0, right? This is minus f of x naught y naught, okay, divided by t. And what is this? This is same as f of x naught plus t comma y naught minus f of x naught y naught divided by t, and take the limit. This is the object. Same thing. So whatever f of, like in earlier slides, limit of h approaches to 0, f of x naught plus h comma y naught minus f of x naught y naught divided by, same thing I am just writing in terms of the point p naught and the vector E1, because you will see later on when I will talk about the functions from Rn to R, then I can have the notions of partial derivative with respect to each coordinate variable. So that is why this notation is useful to talk about that. Okay. So this is the del f del x at x naught y naught. Similarly, del f del y at x naught y naught. Again, since I am talking about the partial derivative with respect to y variable, that means the first variable I should keep fixed at x is equal to x naught, and I want to talk about the derivative with respect to second variable. So it gives a rate of change of f with respect to y at y naught when x is held fixed at the value x naught, like in the del f del x at x naught y naught. Similarly, del f del y at x naught y naught also basically rate of change of f in the directions y directions. So earlier I will have these directions, x directions, now I will have y direction, this direction. So that means this is the vector j from 0 to r. Again you can just write it, f of p naught plus t E2 minus f of p naught. What is this? This is f of x naught plus t comma y naught minus f of x naught comma y naught. Okay. So then same object. So that means the same object I am writing in terms of the point p naught and the vector E2. So therefore, if the limit t approaches to 0, f of p naught plus t E2 minus f of p naught divided by t, if they take the quotients, if that limit exists, then I will say that this is nothing but the del f or partial derivative of f with respect to y at the point x naught y naught. Okay, so these are various notations you will see in many books. So some of the books use some other notations. So this is but all are same. So sometimes it is written that del f del x at x naught, del f del x naught divided by del x, del f del x at x, kind of there is a line. So or sometimes it says that f with respect to x, f suffix x at x naught, or del f del x1 at x naught. Because when I will talk about Rn, so I cannot have xy, so instead I will have x1, x2 up to xn. So in that case, these are the notations will be much more useful. Or d1, so 1 stands for with respect to the variable x1, or d1 of f at x naught. Similarly, fy, so this is for two variable at 2 dimensions, I will have x, y, 3 dimensions I will have x, y, z. If I go for more than 3 dimensions, it is better to give the variable as x1, x2, xn, and in that case, these are the notation much more useful there. These are notations. If I am again I am in 3 dimensions, if I have z is equal to f of x y, then del z del x is also used to denote del f del x, or del z del y is also denoted by del f del y. So these are the notations various books have used. But if I go more than 3 dimensions, I think these are the notation much more useful. Okay, so just now I said, so I want to talk about the partial derivative of f from Rn to R. So that means suppose if I have a function f a subset of Rn to R, where S is an open set and x naught is a point in S, then this is the definition, the first order partial derivative of f with respect to ith variable, or that is the variable xi. So that means since I am in Rn, so it will have a vector consisting of n orthonormal basis. So I am saying that variable is x1, x2, xn. Then at the point x0, y0, I want to talk about the partial derivative of f with respect to xi variable at the point x0, which is nothing but, as I told you in my earlier slides, that this is the notation I can easily extend. So what you have to do, so take the value of f x0 plus t ei. What is ei? Since I want to talk about the partial derivative of f with respect to xi, that means consider the vector ei. What is ei? Ei is the unit vector whose ith position is 1, rest of them are 0. So this is that means, so that means ei is fixed, x0 is fixed, so that means it's a function from t goes to f of x0 plus t ei. So therefore if I take limit t approaches to 0, f of x0 plus t ei minus f of x0 divided by t, I mean if I consider this quotient, if I take the limit, if the limit exists, then I will say that partial derivative of f with respect to xi variable at the point x0 exists, okay, provided the limit exists. Here ei denote the unit vector along the ith coordinate axis. So that means ith coordinate axis, that means xi axis, and the corresponding unit vector is ei, whose ith position is 1, rest of them are 0. The one is the ith place and rest all are 0. So therefore now, so it's very kind of just parallel extension of whatever I have discussed from R2 to R valued functions. That means since I am in Rn, so I will have n variables x1, x2, xn. If I want to talk about the partial derivative of f with respect to xith variable, that means I am in the ith coordinate axis. Consider the vector unit vector ei, whose ith position is 1, rest of them are 0. Calculate the limit t approaches to 0, f of x0 plus t ei minus f of x0 divided by t. Now this makes sense, because what? Because I can easily divide by t, because t is a real number, and of course range of f is real, so this limit you can easily calculate. If the limit exists, I will say that partial derivative of f with respect to xi variable exists at the point capital X0. Again, as I said, various notations people use, like these are the notations useful: del f del xi at the point x0, del f at x0 divided by del xi, del f del xi at x0, f suffix xi at x0, f xi x0, del f del xi at x0, di f x0. So these are the various notations many books have used. So once we have xi fixed, that means I am talking about the partial derivative of f with respect to xith variable, and capital X0 of course is fixed. That point I want to talk about the partial derivatives. Okay, so if del f del xi at x0 exists for each I1 up to n, then f is said to be first order partial derivative as x0. Okay, so that means if I have a function f from Rn to R, so I will have n variables, that means n partial derivative exists, and that I denote it as del f del xi at the point x0. And various notations. So this is, I think, one of the useful notations. So let's see some examples. Okay, as I said, I have to talk about that whether existence of partial derivatives implies the, or we'll talk about the continuity of f and vice versa. Look at the first example. What is the first example? This is the same function f of xy, or f is a map from where to R? F is a map from R2 to R, f of xy, which is exactly equal to xy. Okay, it's a very nice function. It's a continuous function, right? Now look, question: examine the existence of first order partial derivatives of f at x0. And examine the continuity is there, because it is a very nice function, it is continuous function. So I am saying that yes, partial derivative with respect to x, because it's R2 to R, that means I have only two coordinate variables x and y. So partial derivative of f with respect to x exists at the point x0, and with respect to x it is y0, and with respect to y it is x0. You can easily calculate by the definition. So for example, this one. So what is the formula? So limit, so h goes to 0, f of, so at x0 comma y0 I am talking about. So this is x0 plus h comma y0 minus f of x0 comma y0 divided by h. What is this? This is limit h approaches to 0. Okay, but f is given. This is x times y. So that means x0 plus h times y0 minus x0 y0 divided by h. And what is this? This is limit h approaches to 0. So x0 y0 get cancelled. So what we will have? I will have h y0 divided by h, and what will be the limit? Y0, because h get cancelled. What is the limit? So therefore you can easily calculate that partial derivative of f with respect to x at x0 is y0, and partial derivative of f with respect to y at x0 is x0. So that means all partial derivative exists at the point x0, along with my function is continuous. What about the second example? Look, these functions, this kind of functions you are already familiar with in my earlier lectures, that f of xy is equal to xy divided by x square plus y square if xy is non-zero, and at 0, 0 it is 0. Automatically this function is not continuous, right? Because if I take y is equal to mx, right, the limit does not exist as xy approaches to 0, 0. So limit xy approaches to 0, 0, this fxy does not exist. That I already discussed, does not exist. Because you take y is equal to mx path, you will have value 1 by 1 plus m square, and it varies different values of m. So therefore limit does not exist, so therefore it is not continuous. What can I say about the existence of partial derivative with respect to x at the point 0, 0 and at the point 0, 0? Both partial derivative. Of course, it is a function from R to 2R. I will have two partial derivative, one is with respect to x and one is with respect to y. First one you should calculate, just use the formula, that's it. So this is limit h approaches to 0, f of, at the point 0, 0 I am talking about, so this should be h comma 0 minus f 0, 0 divided by h. And what is this? This is limit h approaches to 0, f of h comma 0. So this is my functions. So h comma 0 by 4, this is the 0 value. f 0, 0 is 0. This is by, so this is 0. So its partial derivative of f with respect to x at the point 0, 0 is 0. Similarly, you can also calculate this. So that means this example says that my partial derivative of f with respect to x and y at the point 0, 0 exists and the value is 0. However, my function is not continuous. Earlier one, my function is continuous and both partial derivative exists. Here partial derivative exists at the point 0, 0, but my function is not continuous. Look at another example. Suppose this is a function f of xy is equal to x sine 1 by x plus y if x is non-zero, and f of xy is equal to y if x is 0. Again, this is a function from R to 2R. Now I am making questions. Okay, examine the existence of first order partial derivative at 0, 0 and examine the continuity. By looking at the function, it is continuous function. So I am giving a hint, you can calculate it. So for example, if I want to talk about the continuity at 0, 0, what we have to do? So f of xy minus f of say 0, 0, right? So but f of 0, 0, what is the value? F of 0, 0 value should be 0, right? X is equal to 0, so it is 0. So it comes from here. So therefore this is nothing but what? This is nothing but f of xy. And if I take the some what is called bound, so this is, you can have mod x plus mod y. You can have it. Why? Because f of xy is equal to y, automatically this is, if I take x is equal to 0, this is mod y. And what will happen here? Sine 1 by x is bounded by 1, so the mod x. And this is, you can write some constant time square root of x square plus y square. And again by epsilon delta definition, you will be able to show that this function is continuous functions. What about the partial derivative with respect to x and with respect to y? Will they exist? Okay, so I am saying that partial derivative of f with respect to x at the point that does not exist. Why? Because consider the limit h approaches to 0, f of h comma 0 minus f of 0, 0 divided by h, that's limit you have to talk about. But what is that? This is limit h approaches to 0, f of h comma 0, that means y is 0, it is given, right? So h is non-zero, so that means if I have this one, so then what will happen? So this will happen h sine 1 by h divided by f of h comma 0, so this will not contribute, so divided by h. So what is this? This is limit h approaches to 0 sine 1 by h, and this limit does not exist. So therefore the partial derivative of f with respect to x at 0, 0 does not exist. What about this one? Calculate it. Limit k approaches to 0, f of 0 comma k minus f of 0, 0 divided by k. What is this? Limit k approaches to 0, 0 comma k. So that means x is 0. So that means I will have this value. So that means it should be k minus 0 divided by k, which is nothing but 1. That is given. So that means what I observed is that here my function is continuous. However, the partial derivative of f with respect to x at the point 0, 0 does not exist, because limit h approaches to 0 sine 1 by h does not exist, that we know using the sequential criteria. But the partial derivative of f with respect to y at 0, 0 exists. So now I have various examples where my function is continuous, partial derivative exists, function is not continuous, partial derivative exists, partial derivative does not exist, function is continuous. So if I combine all the examples, so this is the moral. So this is a moral from the previous slide. It says that if I have a function f from a subset of Rn to R, where S is a open set in Rn and take a point x0 is in S, Then partial derivative of f with respect to xi variable at x naught exists for all I does not imply f is continuous at x naught. Similarly, continuity of f at x naught does not imply the existence of partial derivative with respect to xi variable at x naught. So these are mutually independent. So if I have examples where my partial derivative exists, my function is not continuous, or my function is continuous, my partial derivative does not exist. So these two concepts are mutually independent. So one does not imply others. So this is again some algebra of continuous functions, algebra of limits. These are same things. So like if I have two functions f a subset of R into R and g a subset of R into R, or S is an open set, take a point x naught is S. Suppose this is the partial derivative with respect to xi variable at x naught, this is the partial derivative with respect to xi variable at x naught of g exists, then the partial derivative of f plus g with respect to xi variable at x naught exists. Not only that, this is nothing but the sum of the partial derivative of f and g. Similarly, scalar multiplications, if I have f and lambda f, then the ith partial derivative of lambda f with respect to xi variable, lambda will come out. So partial derivative of f with respect to xi variable. Dot product, if I have fg again, so if I both partial derivative with respect to ith variable at x naught exist, then the product, if I take the dot product, again it partial derivative of f with respect to xi variable times the value of g at x naught plus f of x naught, then partial derivative of g with respect to ith variable at x naught. And if I have composition function, this is called the chain rule. That means if h is R to R is differentiable at f of x naught, that means whenever the h compositions of f make sense, f is a function from where to R? F is a function from Rn to R. So that means if I take a function h from R to R, so that means h compose f, suppose it makes sense, then if the partial derivative of f with respect to xi variable exists, and suppose h is differentiable at the point f of x naught, then h composed f, it makes sense, and I can talk about the h compose is a function from where to R. H compose f is a function from, again of course, a subset of Rn to R. So then I can talk about the existence of partial derivatives of the function h compose f. This is nothing but the chain rule. That means the partial derivative with respect to xi variable of the function h compose f at x naught, which is nothing but derivative of h at the point f of x naught, which is given because h is differentiable, exists, times the partial derivative of f at xi variables at the point x naught. So this is chain rule also true. So if I have a function h from R to R, if I have a function from subset S subset of Rn to R, suppose the partial derivative with respect to xi variable exists, and suppose h is differentiable at f of x naught, and simply the composition makes sense, and I can talk about the partial derivative of h composed f with respect to xi variable, and I can write it in terms of the derivative of h at the point times partial derivative of f with respect to xi variable at that point. I think I should stop here. So that's all about the existence of partial derivative. If I have functions from Rn to R, if I have n many variables, then this is the notions of partial derivative, and then it follows some scalar multiplication, dot product, these are the things too. And then I also discussed that there is no connections between the existence of partial derivative or continuity of or existence of, these are mutually independent. So even if my partial derivative exists, will not imply the function is continuous, or existence of partial derivative at some point will not talk about the continuity of it. These are independent concepts. So these are kind of concept of partial derivatives. In my next lecture, there is another concept that I will talk about, that is called the notion of directional derivatives. So there you will see, like here I will have a fixed directions, like if I in R2 I will have two axes, x axis, y axis. So fixed directions I am talking about the notions of derivatives on those directions. So instead of axis directions, if I have just some arbitrary directions, can I talk about the differentiability of my functions in these directions? Answer is yes, you can talk about, and that brings to the notions of what is called directional derivative. Okay, I think I should stop here. Thank you.